So you want to learn how to program on Arduino so that your project can actually do something. Well, this guide will explain how to program Arduinos as well as basic programming concepts. At the end, I'll show you a programming example of an object-avoiding robot, which has a PCB manufactured by PCBWay. More on them later. Alright, so before we talk about the programming itself, we need to talk about the basics of microcontrollers, how they're able to control things like motors or sensors. Here we have a chip of sorts, and it's a microcontroller. Microcontrollers can store instructions on them, which you'd write as a program. With these instructions, microcontrollers can get information from sensors or other forms of input, which are connected to it through some of these metal pins. With this information, the microcontroller can control some output, like an LED or motor, in the way specified by the instructions you wrote in the program. Now, this microcontroller by itself is not an Arduino. This here is an Arduino, and it has that microcontroller on it. Both are functionally the same in that they have pretty much the same inputs and outputs. It's just that the Arduino connects the metal pins of that microcontroller to pin headers on the outside that you can easily insert wires into. Arduinos also have many other components to allow it to work, such as chips to allow the loading on of code, to output serial data, voltage regulation for power, and more. Now, this is a short description of microcontrollers and Arduinos, as well as how they'd work in a circuit. So if you want more information about it and about electronics in general, you can watch my guide on electronics, which is episode 2 of this series. Now on to how to program Arduinos. I'll be using Tinkercad to show the basic programming concepts. Its circuits section is a great start to learning basic electronics, as well as Arduino programming. And it's free too, so I recommend you check it out. Okay, so if you get onto Tinkercad and you want to follow along, you're going to press this code button, and by default it's going to be in blocks, but let's do text. And don't worry, text is not too bad. It's actually pretty simple once you get the hang of it. I mean, of course, I'm the one saying that, but trust me on this. So let's get into this. What is this thing here in the first place? Well, you have the recognizable like LED that you want to light up. And then you have this over here. This is a push button. And whenever you hold down this button, or when you click on this simulated push button, it'll connect this side, the B side, to this side, which is the A side. So essentially, it'll connect this wire to this wire over here. And so what this does is we have 5 volts over here. If we click this, 5 volts would be able to go through this push button and through this resistor right here. Now this resistor, for one, is to prevent a lot of amperage, a lot of current from going directly from 5 volts to ground. And this is very, very important so that we don't destroy anything. And then before that resistor, before the voltage drops, we can take that voltage before that resistor and put it into pin number 4. And we can use that as a signal to turn it on. So what is the point of this right here? When you start to code in Arduino, you have this by default. And of course, this language is in C++, by the way. And for the setup, as the name suggests, you set things up over here, which means that you can tell what pins would be doing what. For example, like if we would want to have an input for pin number 4, we would say pin mode for the pin number and then input. So that basically tells pin number 4 that it has to input some signal and tell us what it is. Similar for pin number 13, except we don't want to input a signal, we want to actually output one. So you can kind of guess what we're going to be doing here. Pin number 13 and output instead of input. And so for this circuit, that's basically all we would need to do. The loop essentially goes on forever. So after we go through this setup kind of section here, it only goes through it once. And then it does that forever until you turn off the circuit. This allows us to continuously update whatever. So I'm gonna just put a delay here, which delays by a certain number of milliseconds. And we're just gonna delay by 100. Now, there's this command called digital write, and writing is a form of output, and digital is, well, digital. And there are other ways to output things like analog and to input in terms of analog as well. So there's analog write, which is similar to digital write. And interesting thing is, these both have to connect to the digital pins up here instead of analog. And then there's digital read, which is similar to digital write, except we input a signal. And then there's analog read, which is used to tell us what voltage level is going into these pins over here. So instead of just on or off, analog read tells us a specific voltage amount. So basically like 3.5 volts or 4.5 volts out of 5. Analog write allows us to write essentially like 4.5 volts. It'll output 4.5 volts. Now it's a digital pin, so it only turns on and off, but it does it by turning it on and off in certain time intervals to make it an average of 4.5 volts, for example. Let's just contextualize all of this. If we digital write to this output here, so basically pin number 13 will have to turn on based on number 4's input. So if we do digital read 4, then essentially what this does is it'll take in whatever the input to 4 is. So if it's 5 volts, this will be on, and so it'll write to digital pin 13 an on state, and that's an output. So if the input is on, then the output is on. So as you can see, I press the button here and it feeds in the 5 volts from over here, and so digital write to 13 will have to be a 1. Okay, so one thing that I want to go over are data types. So if you have int, let's call this LED equals 13. We could also have like a float, and then we'll kind of figure out what each of these are kind of there for. Okay, so if we were to focus up here, we would see int, which stands for integer, LED, which is a variable name, and 13. So int is an integer, and as you might know, integers are like 1, 2, 3, 4, but not 0.5, 0.7, or 1.8 or something like that. Essentially what you do for variables is you define what kind of variable it has to be, and then you name it whatever you want. So I could just do LED like 1 or something, but you can name it whatever you want, and then you can initialize it, essentially setting it equal to a number. Or you could just leave it like this, which would set it equal to 0 by default. Similar thing for a float. So that means that number will be a variable that holds a decimal number. Bool stands for Boolean, and that's basically a true or a false. So we've seen int before up here. Const essentially means that we can't change this at all. It just stores this number, whatever it is, into this variable, and you can't change it. So how would we be able to change what we do here? Well, it essentially allows us to contextualize these numbers right here. So pin mode 4 input, we can replace that with button, and then pin mode 13 correlates to this value here, so we can replace that. And so whenever pin mode is executed and it sees this variable, it's going to go up here, okay, LED, and it'll see the number 13 and plop it in for you. But you will see the letters LED and you'll know what it means. So you can see how I always have to hold down this button to have this LED turn on. If I let go, it turns off. But let's say I'm lazy and I just want to press this button and it turns on forever. And then when I press it again, it turns off. But as you can see, that doesn't happen here. So we use some logic statements like if statements. So if, let's say digital read button, so let's get rid of that. So we take this statement, we read what digital pin 4, which is what button is at. So if this is equal, that's what double equal sign means. If it is equal to 1, now remember, if it detects 5 volts, it'll count it as a 1. If it's 0 volts, then it's, well, 0. You can also say if it's equal to high, which means if it is turned on, or if this pin is turned off, which would be low. So those are equivalent: low, 0, 1, high. And we use some of these curly brackets. Curly brackets are helpful in that you can determine where the beginning and the end of certain functions are. Oh, sorry, and I forgot to mention, after every line of code, you add a semicolon, and that is to help the program know what the end of a line is. Okay, so if we have this, we can use this variable up here. If the button is high, then we would want state to equal true. So state would be on. What we actually wanted is not a one-to-one relationship between pressing and on and then not pressing and off. We want, if we press and then we let go, it turns on. And if we press down again and then let go, it turns off. So how would we do this? Well, we would use something called a while loop. So if digital pin is high, essentially what we want to do is when we press down, it turns on, but then we want to wait for when we let go. So how do we wait for when we let go at this point? So we would use a while loop, which essentially would keep looping within itself until something happens. So there's multiple ways of doing it, but we're going to use the while loop here. So while this, so if we press the button and it turns this pin on, then while it is high, then we're going to do something kind of interesting here. We're going to do nothing. Or you can kind of imagine we're just going to do that. It's going to wait, and then when it turns low, so essentially when we hold down this button, it's going to keep looping through this statement forever and ever until I let go. Until I let go of that button. And essentially it's going to loop through doing absolutely nothing. So as we hold down the button, it's going to loop through this forever. And then when we let go, it's going to set the state to true. What we can do is do digital write to that LED, output to the LED, the state value. So let's just see if this works here. So I press and then I let go and it turns on forever. Now, how would we distinguish between pressing and then letting go and pressing and then letting go again? They're both the same exact thing, but for one of them, the LED is on, and for another, the LED is off. Because as you can see here, we press and let go, but how do we know when we press and let go again, it has to turn it off? Well, there's a difference in both of these states, because here the state is on, or the LED is on, so we can use this variable to differentiate between pressing and letting go. So, and we need state is equal to false. So this is for when the LED is off from the start, and then we try and turn it on. We're going to copy this whole thing here. So if digital button is equal to high, and the state is equal to true, so this is when it's already on, and we press and let go to turn it off. So then that's why we go back down here to false. So let's just see what this does. Hopefully it works. So I press and let go, it turns on. And so that means that the state is true now. So when I press down and let go, it's going to activate this if statement, and it'll go through this code right here. So if I press and let go again, then it should turn off. If you want to see what state the LED is in, and you want to see it in a serial monitor like this, what you would do is you would have serial.begin, just type that in, 960. That's 960 baud, and that's essentially like a refresh rate, if you want to think of it like that. And serial.begin basically starts the serial communications between our board and our computer, which is simulated here. Now, what we want to do is we want to go down here and print what the state is. So for you, serial.print, ln is print line. So every time we print a value, we make a new line. We basically use the return key or enter key essentially. And you'll see what I mean by that. And then we want to print the state. So very simple there. So it's all zeros. And then when we hold down and then release, it all becomes 1. So that's on. If we hold and then release again, the LED state is off. Now, if I didn't put the ln there, this is what happens. It's going to go all the way across like this. So it doesn't make a new line. Okay, so we're going back to this Arduino programming example here, and you can see there's quite a bit of stuff here, but a good amount of it is actually just comments, these orange things here indicated with the double slash, just trying to explain what each group of lines does. So you can sort of recognize how up here we have the variables that we would put into other functions. So we contextualize each of these pin numbers into their respective names, and then we create another variable type that isn't constant, because we're going to need to store the distance in centimeters and also the travel time of the ultrasonic wave from to the object and back in microseconds. And then here we, as we've seen before, we do the setup, and then we begin the serial communications so that we could see what's on here. And that basically gets us halfway of the code, or halfway to the end of the code, which essentially is just turning the trigger pin off, and then we wait a little bit just to make sure it's off. And then we turn it on for 20 milliseconds, and then we turn it off again. And that sends out an ultrasonic wave from this sensor. So then it goes out, it comes back, and then the echo pin, as the wave is traveling, has been on this entire time. And it turns off when the wave comes back. And so the pulse in function is just another function. Basically takes in a parameter called the pin parameter, I guess, is what pin it should be looking at. And high is basically recording how long the signal turns high for. Basically, that's what the echo pin does. It turns on right when the trigger pin sends out an ultrasonic wave, and then it stays on until the wave comes back. So we're able to get the duration of the wave, or the travel time of the wave, from this function right here. And that outputs a time in microseconds. And so we just say that there so that we remember what it is. And then we calculate the distance. So we know the speed of sound That's how fast the ultrasonic wave travels. This is the speed of sound in meters per microsecond, so we multiply by the microseconds. But that gets us the distance of the round trip, but not one way, which is what we want. So we divide it in half, and then we multiply by 100 to get centimeters. And then we just print that out, and that's what happens here. In addition, we use analog write. So I didn't cover this before, but this is similar to digital write, except if you use one of these pins right here with the curly bracket, or not curly bracket, the tilde, then you can send out a varying voltage signal. So instead of it being completely 0 volts or 5 volts, it'll be between 0 volts and 5 volts. So it could be like 3 volts or something like that. And the maximum value that you can put into this spot right here is 255. So that's why we multiply by 255 here. And the thing before that is the percentage of distance between no distance and a arbitrary 350 centimeters. So if the distance was recorded as half of this, then we're gonna have half of 255, which indicates half of 5 volts. And because it's a function of that, we can change the brightness based on object distance. Now, if we were to go to, instead of using the LED and actually replacing it with a motor circuit, like this right here with a motor driver IC that we've seen in the circuits video, then we'll be able to vary the motor speed. So it's a pretty similar concept here. Ultrasonic sensor code, that part of it is exactly the same. As you can see here, exactly the same, except we have 2 different write functions. One of them is the digital write, sets 1 pin to low. And I've explained this circuit before. Essentially, we're able to control this motor through controlling the signal through 2 wires, which goes into here, and it powers this motor based on these 2 signals. So I explained it in depth in a previous video, but the concept is still the same, where we're able to take a distance input or distance measurement and use analog write to create a varying RPM in this case. So it's slower and then it spins faster with more distance. Now we will take a look at programming this object avoiding robot. In the previous videos, we have designed and manufactured the chassis, as well as the PCB, thanks to PCBWay, the sponsor of today's video. Arduinos are made as a PCB, and perhaps you'd need a PCB of your own project as well. If that's the case, you can use PCBWay's PCB manufacturing services to get your PCB made. Ordering your PCB is simple. You just drag and drop in your generated PCB design files and select the parameters that you want. The default options are good for most DIY projects. You can then take a look at the price and shipping times. Once you're happy with the order, you can send it in for PCBWay to check any errors. Once they approve, you can order the PCB and have it at your doorstep within a week. PCBWay can also manufacture your 3D model designs using 3D printing, CNC milling, sheet metal manufacturing, and more. Alright, so back to programming this robot. The demonstrations that we did previously used Tinkercad, which is all just a virtual simulation. To program a physical Arduino, you need to download their software from their site. After downloading and accepting the default options, you can connect your Arduino to your computer via a USB cable. Then you can go up top to this tab and select the port. It should show only one, and type in the kind of Arduino board you have. Alright, so let's go over the programming of this robot. Okay, so object avoiding robot code. There's quite a bit going on here, but you can pretty much follow along because it's pretty similar to the smaller circuits, but just a lot more stuff and a lot of the same kind of stuff, where we have, instead of 1 ultrasonic sensor, we have 3. So that's why we have 3 of the same kind of things here. And then we have the motor pins. So as before in the PCB episode, we showed this circuit here, and the Arduino's outputs are connected to this motor driver, and that's reflected in the code. Same exact names on the schematic as well. So we use these outputs and these inputs to control the entire robot. So we set them as such. And then we also set up some variables to keep track of what steering direction we would want to go in terms of a number. That will be shown later. And then a turning constant, which kind of encodes like the strength that we would want to turn with based on the ultrasonic sensor inputs. So this is the same exact code as used in the Tinkercad examples for the circuits, as well as the programming examples with the ultrasonic and LED, or ultrasonic and motor, but they effectively use the same exact ultrasonic sensor code segments. And basically this function takes in the trigger pin numbers and the echo pin numbers of your ultrasonic sensor. So for example, down here, we use trig1 and echo1, which correlates to, I believe, the right ultrasonic sensor, the rightmost one, whereas trig3 and echo3 would be the leftmost. And so we're basically able to specify which ultrasonic sensor we would want to get a distance from with this function. And then, of course, it returns what distance it actually is for that specific sensor. So instead of needing to, copy and paste this 3 times in the loop, we just write it once in a function, and then we just write that small amount of text, that function, many times. So that's why it's so helpful. The new function, or the new type of code, or I guess code segment, would be this one, which essentially controls the motor outputs that go into the motor driver integrated circuit, that little chip on there. So we put in a left speed. Basically, this dictates the speed on the left side of the robot, so the left motors, and then this dictates the speed of the right motors, so motors on the right side of the robot. And we're basically doing tank drive, which is what the function is called. So basically, like, one side goes forward, the other side goes back, so then we start rotating. So yeah, if the speed is positive, then we set the corresponding pins positive, and then the other side would be low. You kind of try and figure out why we need this. So we're using a PWM pin for an input into the motor IC driver, or motor driver IC, and that would allow us to control the specific speed of it instead of just going full speed all the time. So that's what this is for. And then if the speed is negative, then we would set the other side low as compared to high, and then we would treat this as a normal, like, positive input. So here it would be a negative input, here it would be a just normal positive input. It's kind of complicated to explain, but you can kind of try and figure out that yourself. And then the same exact thing for the right side, except it's on the right instead of the left. And that comes with different pins and stuff like that. So then we'll go into here, and essentially this part right here is a little bit complicated, but the stuff up here is less so. So basically, if any of our ultrasonic sensors, this one, so like the right one or the left one, is below 30 centimeters, and this is an or statement, so equivalent to saying or, like that. So if this is less than 30 centimeters or this one is less than 30 centimeters, then we calculate a steering direction. And this steering direction is essentially added to the left side and then subtracted from the right. And this steering direction is essentially how much we need to turn right. So if this number is positive, like positive 100, then we need to turn right positive 100, whatever that means. But if it's a negative number, then we need to steer negative 100 to the right, which is left. And that's basically why we have this right here. And so yeah, we basically calculate that by getting the difference between the right sensor and the left sensor, and then multiplying by our turning strength, which is sort of how I think of it. If we make this lower, then we are less sensitive and less strong in terms of turning. But if we do that, then we add more power to the motors to steer faster. That's just a way for us to tune our turning. K just stands for a constant, and then P stands for a proportionality. So proportionality constant. Let's test this thing out. Take it for a drive. Well, actually, we're not driving it. It's driving itself. Ultrasonic sensors generally work on flat objects pretty well. It's questionable if it's like curved or something like that. And so far, it looks pretty good. Oh boy. Yeah, sometimes it gets itself stuck. I've linked all the files in the description for the object avoiding robot for you to take a look. And that concludes this video as well as the entire series. I really hope you guys enjoyed it and were able to get started on your DIY projects. Welcome to the world of creative DIY engineering.